Picture this, you are in a bustling city filled with dazzling light and countless routes. And how do you find the fastest way to your destination? In this video, we are tackling a coding challenge that brings the magic of graph theory to life. Join me as we explore the city of blinding lights and discover how to calculate the shortest path between cities. You'll be able to navigate the maze before the lights goes out. Let's find out. Have you ever felt overwhelmed by choices while trying to get from point A to point B? What if I told you that there is a clear way to find the shortest path through a complex city? In this video, we'll unravel a fascinating coding challenge from the city of blinding lights together. So we'll learn how to map out the quickest route using Floyd's algorithm. Are you ready to shine a light on the best parts? Let's jump in. Alright, now that we have set the stage, let's dive into the heart of this problem. The task is to find the shortest path between cities in a network, and we'll be using something called the Floyd-Warshall algorithm to accomplish this. So let's walk through the logic step by step, like we are brainstorming together at a whiteboard. First off, we begin by reading the input, which tells us two crucial pieces of information denoted as n and the number of rows or edges denoted as m. This is our foundation, the building blocks that helps us model the network. Next, we need to establish a distance matrix. Think of this as a giant table where each cell represents the distance between two cities. Initially, we set the distance from a city to itself as 0 because, well, it doesn't take any distance to reach yourself. For all other pairs of cities, we set the distance to infinity. Why infinity? Because we want to indicate that these cities aren't connected yet. It's like when you first move to a new place and you have no idea how to get around everything else. So infinitely far away. Once we have our distance matrix set, it's time to read the roads. For each road, we'll update our distance matrix to reflect the actual distances. If there is a direct road between two cities, we'll enter the distance in a matrix. But there's a little twist. If we find the distance, the current distance for the road, for that road is greater than the new one we are reading in, we'll update it. This ensures that we always have the shortest known distance between any two cities, right? So here's our matrix. Now we have established a direct connection, but what about those indirect routes? That's where the Floyd-Warshall algorithm really shines. This algorithm iteratively checks if the path through an intermediate city is shorter than the previous known direct path. If the path to an intermediate city is shorter than the previously known direct path, picture this like a detective piecing together evidence. If city A can reach city C through city B faster than directly, we update our knowledge. We'll repeat this process for each city, ensuring that by the end of the algorithm, our distance matrix holds the shortest path between all pair of cities. After running this algorithm, we have a complete view of the shortest distance, but we are not done yet. We'll still need to handle the queries. Each query asks for the shortest distance between two specific cities. All we have to do is to look up the distance in our matrix. If the distance is still set to infinity, it means those two cities aren't connected. So we'll return -1 to indicate that. So to recap, we start with our basic input, build a distance matrix filled with potential paths, use the Floyd-Warshall algorithm to ensure that we capture all the shortest path, and finally we answer the queries based on our comprehensive distance matrix. Each step is crucial, and together they form a solid approach to solving the problems. Alright folks, let's wrap up what we have covered today in today's coding adventure. We tackled the Floyd-Warshall algorithm. We found the shortest path in a network represented by cities and roads. We started by initializing a distance matrix to manage the distances between each pair of cities, setting them up to infinity except for self distances, which are 0. Then we populate our matrix with the weight of the edges, ensuring that we only keep the shortest distance. Finally, we implement the core of the Floyd-Warshall algorithm to update our matrix and answer the queries for the shortest path between specified city pairs. The key takeaway here is the power of dynamic programming in graph algorithms, and by systematically updating the distance, we can efficiently find the shortest path between any two nodes in a weighted graph. If you have enjoyed this deep dive into algorithms and problem solving, don't forget to give it a thumbs up and subscribe for more content like this. We have got more exciting topics lined up in graph algorithms and optimization techniques. So let's take your coding skills to the next level, and make sure to check out the link of the source code in the description below. Stay tuned and happy coding.